Every night, human biology initiates a controlled experiment where the conscious mind is isolated from its physical environment. This is the state of lucid dreaming. During a lucid dream, the physiological baseline of the organism shifts. External sensory input is suppressed, closing the standard informational channel between the brain and the world. Simultaneously, the physical body undergoes sleep paralysis. The organism is motionless, removed from immediate environmental demands or adaptive pressures. Despite this isolation, the dreamer navigates three-dimensional space and experiences vivid perception. Modern neuroscience often explains this by describing the brain as an innate virtual reality generator that constructs immersive worlds during sleep. Physicalist theories extend this further, suggesting that waking life is simply a form of online dreaming, a simulation constructed by the brain that happens to be constrained by sensory feedback. But if the brain acts as an autonomous rendering engine, we face a question of origin. Why does the system produce more complex experience when it is doing less, with sensory input gated and the body paralyzed? This assumption of an autonomous neural rendering engine faces a significant challenge when we compare the richness of dreams to the reality of waking sensory deficits. This challenge is known as the rendering dilemma. It highlights an asymmetry between what the brain supposedly does while we sleep and how it actually behaves during waking life. The sleeping brain is credited with the power to render detailed, multisensory environments from internal resources alone, without any external data. Yet, during waking life, perception degrades directly alongside the sensory organs. In conditions like macular degeneration, a deteriorating retina leads to a blurred or failing visual field. As the schematic shows, the brain acts as a passive conduit, its output rigidly mirroring the degraded signal. If an internal rendering engine builds cities in our sleep, it should compensate for a failing retina. Despite decades of visual data, it fails. Waking perception does not use an internal generator to fix the image, it transmits the biological failure. This suggests that the brain's role in experience is not to generate content, but to filter and channel it based on the constraints of the sensory input it receives. To understand this distinction, we can view the relationship between the brain and consciousness through a hardware-software divide. The physical brain provides the architectural hardware. It sets the rules for spatial geometry and the processing limits of the visual system. These architectural constraints persist even in sleep. The brain's representational infrastructure imposes its signature on the dream, much like a game engine's capabilities limit what can be displayed on a screen. Conscious awareness provides the phenomenal content that fills this architecture. During waking, this content is strictly filtered to match sensory reality. In a dream state, the sensory filter loosens. Without external data constraints, the content of experience is no longer bound by physics or causal regularity. Lucid dreaming reveals consciousness operating the brain's hardware in a more autonomous mode, providing a clearer look at what belongs to the mind versus the brain. This division is marked by 4 specific signatures. The first is intention responsiveness. In a lucid dream, internal expectations and beliefs directly shape the experienced environment. When a dreamer decides to fly, the dream world reconfigures in response to that intention. This is an observation of mental causation acting on phenomenal content. While physicalist models describe this as neural modulation, the subjective experience is one of direct authorship over the perceived world. The second signature is the vividness surplus. Empirical findings show that dream imagery is often significantly more vivid and immersive than deliberate waking imagination. This creates a puzzle. The same system produces a richer qualitative output while operating with the reduced neural resources and lower activation levels typical of sleep. From a filter perspective, this surplus is expected. During sleep, consciousness no longer competes with the heavy cognitive load of processing constant sensory input, allowing it to render through the brain's architecture with less restriction. The third key signature is phenomenal completeness. Dreams provide a fully integrated, multi-sensory world. The mind generates the binding of features into coherent objects and spatial arrangements without any external data to guide the process. This demonstrates a double dissociation. Just as blind sight shows the brain can process information without experience, dreaming shows experience can exist without sensory input. The fourth key signature is metacognitive sovereignty. This is the moment the dreamer recognizes the state of their own experience, making the judgment, "I am dreaming." Biologically, this is an anomaly. This high-level self-awareness occurs while the neural conditions that normally support such judgments, like full prefrontal activation, are largely absent. While frequent lucid dreaming is associated with increased connectivity in the brain, it is the dreamer's initial recognition of the dream state that serves as the catalyst for these structural changes. This suggests that the capability to reactivate metacognition resides with consciousness, with the physical neural accommodation following as a result of that repeated mental exercise. These signatures challenge the view of epiphenomenalism, the idea that consciousness is a passive byproduct of brain activity with no causal power of its own. If consciousness were truly inert, the dreamer's sense of control would be an illusion, a feeling running in parallel to neural processes, but never actually directing them. Communication studies complicate this passive view. Researchers have shown that lucid dreamers can receive novel questions during sleep, process them, and respond intentionally using eye movements. Further evidence comes from creative problem-solving. Dreamers who actively incorporate a puzzle into the phenomenal content of their dream solve it at a rate of 42%, compared to just 17% for those who do not. The cognitive success is tied directly to whether the puzzle was experienced within the dream's narrative. If phenomenal experience were merely a byproduct, the specific content of the dream would be irrelevant to the cognitive outcome. This correlation between experience and results aligns with the model of bidirectional interaction, where conscious experience plays an active role in cognitive processing. To explain how a non-physical mind might interact with a physical brain, some dualist frameworks point to the microscopic level of quantum indeterminacy. In this model, consciousness influences neural activity by biasing outcomes within the margins of uncertainty allowed by physics. This would explain why dream control is often variable. Consciousness is not overriding physical law, but operating within the probabilistic window that the brain's architecture provides. Under this framework, the brain is not a generator of experience, but a sophisticated biological filter, an evolutionary tool designed to constrain consciousness to the immediate needs of survival. During waking, the filter is tight, tethering us to sensory reality. During a lucid dream, that tether is loosened, and we see the mind rendering reality through the brain's architecture with its own resources. The evidence of the isolated mind suggests we aren't biological machines simulating a self, but an independent consciousness experiencing the world through a physical lens.